Chapter 7, Sample Variability. This is a short chapter with just 3 sections. Theoretically, it is important though. We talk about something called the central limit theorem here, which is the fundamental theorem of statistics and provides the theoretical background of the inferential statistics, which we will begin here in this chapter and continue until the end of the semester. Now, what is so-called the inferential statistics? Well, it's a vast topic, and as I said, we are going to start now and continue until the end of the semester. And that means it is impossible for me to explain it in 1 or 2 sentences right here. What I can do is to show you one aspect of it. The simplest aspect of the inferential statistics must be a prediction, and that, by the way, is the main topic of 7.3 of this chapter 7. How does it work? Let's begin with this picture. Somebody is trying to measure the size of a coffee bean here, and we have a lot more down here. Let's suppose we have a big bag full of coffee beans, maybe tens of thousands. To measure them all, that's crazy. So what do we usually do? We usually take a random sample of 20, 30, 50, maybe 100 and find out the sample mean. Assuming there is no systematic bias, that sample mean will be the best point prediction, the best point estimate of the real value, the real average coffee bean size of this entire bag full of coffee beans, which we call population mean, by the way. Even though these are coffee beans, not people, we still use the term population in mathematics, by the way. So much we know, by the way. We already studied mean and sample mean, population mean, expected value, those kind of things in chapter 1, 2, and 4, and 5 many times. What's new here? Well, we're gonna add one more question. How confident are you about the point prediction you just presented? Depending upon so-called confidence level, which we will discuss in a little more detail in 7.3, you're gonna get a certain margin of error, plus or minus something, give or take. Consequently, we are gonna get a certain interval, which we will call the confidence interval. This is an example of so-called the interval estimate, which we mentioned in chapter 1. Confidence interval is not the only interval estimate, by the way. There are other kind of intervals that we have to work out, like prediction intervals and tolerance intervals. There are more, but for now, let's stick to the confidence interval. And finding that confidence interval is one of the key objective of the inferential statistics. I said one of the key objectives. There are some other things that we cannot really discuss for now. Anyway, that's something we are going to have to discuss in chapter 7, especially 7.3, but only to a certain degree, because kind of examples we can deal with in 7.3 is a little bit limited because we did not introduce all the necessary tools yet. Consequently, every single example that we are going to go through in 7.3 will be repeated in far more detail with far more general way in later chapters, chapter 8, 9, 10, and so on and so forth. In other words, in terms of practicality, the importance of 7.3 is a little bit limited. You can regard it as the kind of preview of what's come, or a stepping stone toward a little bit harder type of inferential statistics, but that's about it. Theoretically, however, it is important because it is related to, as I said early on, the fundamental theorem of statistics, or the central limit theorem. So I'm going to emphasize a little bit more on 7.1 and 7.2, where we see those central limit theorem, and we're going to see those using the sampling distribution, sampling variability. What am I talking about? Let's continue this discussion in my Mathematica notebook. And here we go. What do you mean by the sampling distribution? The key word here is repeated sampling. The distribution of values of sample statistics obtained from repeated sampling is called a sampling distribution. You see, the sampling itself is a repetition as a matter of fact. If you have a random sample of 100, that is obtained by repeating random selection of an individual 100 times. Now, if you repeat the random sampling of 100 another 100 times, then that's what this repeated sampling is all about. Basically, it's a repetition of a repetition. Now, you may ask this question: what is the difference between 100 repetition of the random sampling of 100 versus one random sample of 10,000? Yes, 100 times 100 is 10,000. We are talking about the same number of individuals. What's the difference? It'll turn out there is a tremendous deal of difference. The repeated sampling, if the number of repetition grows, you're going to have a certain pattern, and that pattern is governed by, well, a lot of different aspects, but one aspect that really stands out is the central limit theorem. No matter where we start, no matter what kind of probability distribution we begin with, the distribution of the sample mean follows the normal distribution if there is sufficient number of repetition. That is the essence of the central limit theorem. And if you have just one random sample of really large individuals, you cannot use that central limit theorem because one is far from, going to infinity. It's not that big. But if you repeat random samples, say 100 times or even more, then you see a definite pattern. We'll see some visualization of those in some of my Mathematica programs here in this section of this notebook. By the way, the sample variability and sampling distribution depends upon the type of sample statistics. And I talked about the central limit theorem, but that's about the mean. And mean is the most important, yes. But there are some other things too, like standard deviation, which follows chi-square distribution. Okay, we're going to talk about chi-square way later, way back, so you don't have to worry about it just yet. And then, of course, there are some other statistics too. And my aim is to show you some of them. Okay, let's go ahead with some action. And let's look at some range distribution. I found this example from our textbook. And let's suppose we roll a pair of dice, 100 times, and then record its range. Highest number minus lowest number. The highest it can be will be 6 minus 1. That's going to be as big as 5. And lowest one will be 0, because if those two numbers are the same. So that's the range. Range is between 0 and 5. And if you repeat rolling a pair of dice, 100 times, and this is a hypothetical situation through random generator, pseudo-random generator embedded in this Mathematica program. Let's repeat this again. As you can see, we have very different histograms showing up each time. Is there some pattern? Difficult to tell. But if we increase the number of repetition, let's see what happens. Do you see a definite pattern? Oh yes, because we have this kind of nice linear decrease and doesn't change much each time I run. Let's increase the number of repetition to 50,000. Not much change. In short, we just found out a definite pattern here. Now here's another example. Choose a pair of integers between 0 and 20 a number of times, and let's repeat it 100 times again. Select a pair of numbers, select a pair of numbers between 0 and 20, and then the range, largest minus smallest, and repeat it 100 times. Here's a histogram, and then let's repeat it. I don't see any pattern. Change too wacky. But let me increase the number of repetitions to 10,000. And I now see a definite pattern. You see, if I run number of times, the change isn't that big. Let's increase this number of repetition to 50,000. A definite pattern. We have this linear decrease, and the change doesn't take place very much, even if I run this program a number of times. Here's another situation. Roll 4 dice 100 times and record the range. Highest minus lowest. We have this kind of situation. Do we see a pattern? Oh, of course, I see a pattern because I'm running this program with 10,000 repetition. Let's go back to 100 repetitions. Okay. There is some pattern, but I don't know, maybe I'm biased because I already saw the pattern in advance when it was set previously as 10,000. I don't see much change. Let's go back to the 10,000 repetition. There is a pattern, a little bit asymmetric, skewed to the left. How about next picture? Choose 5 integers between 0 and 20 and repeat that, let's see, say 100 times, and then find out the range. How about that? Do I see any pattern? Hard to tell. Maybe there is some kind of asymmetric kind of picture. Let's increase the number of repetition to 10,000. Do I see a pattern? Oh, definitely I do. And as you can see, even if I run this randomized program a number of times, the shape, the outline of the histogram doesn't change very much. There is a concrete pattern forming. And that is the case for range, but more importantly, that is case for the number of repetition. The more repetition we take, the more concrete pattern we get. It happens to be range early on, by the way, and this kind of histogram we saw before is an example of a histogram that is skewed to the left. Okay, another example of sample variability. Let's this time roll a die a number of times and record its outcome and repeat 10 times, just 10 rolls, and then as you can see, change is rather drastic. Increase it to 1,000, and now you see a pattern. They're pretty much uniform. Increase to 10,000, and certainly they're uniform. I mean, the probability is 1/6, the same for everything. That's the frequency. How about this one? Roll a pair of dice a number of times and record the sum and the product. Describe this data with histogram, and let's see. Let's go back to a small number first. 100 repetitions, and do I see any pattern? Difficult to tell, and they always change. But if I go to 10,000 repetitions, and the sum in the left hand side shows a definite pattern, it is normal. Product, it doesn't change much, so there is definitely a pattern, but I don't know, I just don't recognize it. But in any case, the moral of the story is clear. The bigger the n value, the bigger the number of repetition, the more concrete the pattern will be. Now let's go with the sum and the average. Roll 4 dice 100 times and record the sum and the average. Blue is sum, red is the average. Do you see any pattern? Difficult to tell with just 100 rolls. Let's increase the repetition to 10,000. Do you see a pattern? Oh, definitely. We are looking at the normal distribution. The central limit theorem in action. Now, how about the next example? Choose 5 integers between 0 and 20 a number of times. Let's repeat it 100 times and then find out the sum and the average. Do you see any pattern? Nothing much, but if I increase this number of repetition to say 50,000, do you see a pattern now? Yes, most definitely. You see a normal distribution. The central limit theorem in action.